Are you guys so excited? These are my favorite problems in this chapter. I love them because they're like puzzles. Let's look at our first puzzle. Air is leaking out of a spherical balloon at a rate of 3 cubic inches per minute. There's my first thing I'm going to underline here. It says a rate. Whenever I see rate, that should tell me that it's going to be something d over dt. Okay, that's always some rate. Air is leaking out of a spherical balloon at a rate of 3 cubic inches per minute. That's my volume. My volume is decreasing 3 cubic inches per minute. When the radius is 5 inches, so when r is 5, how fast is the radius decreasing? How fast, that's a rate, is the radius decreasing? That tells me I'm looking for dr dt. Okay. Where r is my radius, and I want to know how fast is the radius decreasing. So I've identified all the numbers in my problem. I have identified what I'm looking for. Now what I need is an equation that relates v and r for a sphere. And that sure sounds like the volume of a sphere, which is 4/3 pi r cubed. You need some formula from geometry that relates the variables you have. It's almost always just some simple geometric formula. And here we're talking about the volume of a sphere. So v equals 4/3 pi r cubed. Now what you do is you take your formula and you differentiate it with respect to time. So I want to take the derivative with respect to time. This is where your implicit differentiation and seeing that chain rule applied comes into play. If I take the derivative of v, I'm just going to get 1, but because v is not t, I have to follow the chain rule and put dv dt. Moving on to this side, if I take, let's see, 4/3 pi, that's just a constant, so I'm going to multiply that by 3. So I have 3 times 4/3 pi, subtract 1 from my exponent. And then once again, r does not match t, so I have to follow my chain rule, and that's dr dt. Never start plugging in numbers before you differentiate. I have to differentiate first, and then I can start plugging in all this information that I know over here. Let's clean this up a little bit first before we do that. So I have dv dt equals 4 pi r squared times dr dt. Now let's plug in what I know. dv dt is -3 equals 4 pi, r is 5, and I'm looking for dr dt. And this looks good. I have one equation and one variable that I'm solving for. So if I get dr dt by itself, I'll take -3 divided by 4 pi r squared, and we'll simplify that just a little bit. -3, let's see, 5 times 5 is 25 times 4 is 100. Now don't put a box around your answer until you have given this units. Think about what your units are. It's asking for how fast is the radius decreasing. I'm in terms of inches and minutes, so my radius is decreasing, that's my negative, 3 over 100 pi inches per minute. Do not give me an answer without units. Wasn't that fun? I know it was. Let's do another one. A 13-foot ladder leans against a vertical wall. Before I go any further, I'm drawing my picture. There's my wall, there's my ladder, My ladder is 13 feet long. If the bottom of the ladder is slipping away from the base of the wall, so the bottom of the ladder is moving this way, at the rate of 2 feet per second. So that's telling me if I call this distance x and this distance y, this rate of 2 feet per second tells me my rate, so it's dt, dx dt, is increasing at 2 feet per second. How fast, so I'm looking for a rate, is the top of the ladder moving down the wall? So I'm looking for the rate that this is changing, so dy dt equals what? When the bottom of the ladder is 5 feet from the base. So when x is equal to 5. I've identified all my numbers, figured out what I'm looking for. Remember, anytime you see the word rate or speed, that's something dt. Now I need a geometric formula that will relate all these variables together. I'm looking at the sides of a triangle. I'm thinking that's Pythagorean theorem. X squared plus y squared equals hypotenuse squared. Here's my hypotenuse. It's a constant. It doesn't change. That means it doesn't need to be a variable. So I can go ahead and say that that's 13 squared. So I have x squared plus y squared equals 13 squared is 169. I have my equation. Now let's take the derivative with respect to time. The derivative of x squared is 2x dx dt, because x doesn't match t, plus the derivative of y squared is 2y. Y doesn't match t, so 2y, dy dt, equals the derivative of a constant is 0. It's a pretty good looking equation. Let's plug in what I know. The problem said when x is equal to 5, so 2 times 5, and dx dt is this 2 feet per second, so dx dt is 2, plus 2 times y. I have a y and I have dy dt, that's two variables. I'm looking for dy dt, so I need to plug in a number for y. How am I going to get it? I'm going to use my formula. I've got a formula here for finding y. I know what x is. X is 5 plus y squared equals 169. 169 minus 25 is 144. Take the square root, and y is 12. So I got around that issue. So y is 12. I'm looking for dy dt, and now I have a nice equation to do so. Let's simplify this. 2 times 2 is 4, times 5 is 20, plus 24 dy dt equals 0. So I have 24 dy dt equals negative 20. So dy dt equals negative 20 over 24. I can simplify that, divide top and bottom by 5. Nope, divide top and bottom by 4. Am I done? You should be screaming no, because what am I missing? I'm missing my units. It gave me the rate for dx as feet per second. dy is going to be the same thing. 5 over 6 feet per second. Wasn't that fun? I really do love these. Here's the thing you've got to remember on these. You got to remember, whenever you're taking the derivative, you've got to include your dt terms. And then the other thing is, don't start plugging in numbers until after you've done this step where you take the derivative. Those are the two most common mistakes on these problems. Don't forget your chain rule, and don't plug in numbers until after you've taken the derivative. Let's do one more, just because we're having so much fun. A cone-shaped paper cup is being filled with water. I feel a picture. I want to see a picture. I've got a cone-shaped cup, and I'm filling it with water. So there's some water in here. Okay. It's filling with water at the rate of 3 cubic centimeters per second. So the volume of the water, we'll call that dV dt. Actually, I'm going to keep going with the light blue here to represent the water. dV dt is increasing at 3 cubic centimeters per second. The height of the cup is 10 centimeters. So the height of the whole cup here is 10. And the radius of the base, so the base of my cone, is 5. Okay, and those are both of the cup, not of the water. How fast is the water level rising? So fast, so it's going to be something dt, is the water level rising. So I'm looking for dH dt of the water. I'm using the light blue to represent the water. That's what I'm looking for. When the level is 4 centimeters. So when the water level, light blue, is 4 centimeters. Okay. This looks like some extra information. We'll see if I'm going to use that later. I need a formula that will relate volume and height of a cone. I need the volume of a cone, which is 1/3 pi r squared h. Okay. Now here's the issue. I see an r in this formula, and I don't have any information about the radius or the rate that the radius is changing. If I take the derivative of this with respect to time with two variables, I'm going to have a product rule, and I just really don't want to deal with that if I don't have to. So that makes me think, well, what can I do with this extra information that they gave me? Would you agree that the cone of water here is proportional to the big cone of the cup? It is proportional. So what I can do with that is I can look at the dimensions of the cup and see how that relates to the dimensions of the water. Looking at the cup, I see that the height is twice the radius. So of the cup, the height is equal to 2r, or r is equal to h over 2. That's true for the cup, and it's going to be true for the water. That proportion is going to hold true. So what I can do with this r is I can say r is equal to h over 2, and I can sub that into my formula before I take the derivative with respect to time. So I've got 1/3 pi, and then instead of r squared, I'm going to do h over 2 squared times h. We'll simplify that. This is the same thing as h squared over 2 squared. And so let's see what I do with my constants. I have 1/3 and then a 1/4 over here. So 3 times 4 is 12. So that's 1/12 times pi h cubed. That looks like it'll be nice to take the derivative of, and it'll give me the information that I need. So let's do that. I have v equals, we'll say that's pi over 12, keep our constants together, times h cubed, and I want to take that and differentiate it with respect to time. The derivative of v is 1, because v does not match t. I've got to do a chain rule, dv dt, equals, I'm going to take my 3, multiply it out front, so I have 3 pi over 12 h squared. H doesn't match t, so I have to follow my chain rule, dh dt. And that looks pretty good. We can simplify that a little bit. dv dt equals pi over 4 h squared dh dt. Let's start plugging in what we know. dv dt was 3 h was 4, and we're looking for dh dt. So dv dt was 3. Have my constant. H was 4. And I'm looking for dh dt. And I can solve this. 3 equals, let's see, this will be 16 over 4, which is 4. So that's 4 pi dh dt. Divide both sides by 4 pi. And dh dt is equal to 3 over 4 pi. Am I done? You should be yelling no, I need units. And it looks like I need centimeters per second. Too far. Centimeters per second. And we are done. So, identify all your numbers in the problem, figure out what you're looking for, find a geometric formula that describes the situation, take the derivative with respect to time, and then plug in numbers and solve for your unknown.